Hi everyone. Now let's look at the implementation of binary search algorithm that we have just discussed. So what we said we will get the array, we will get n, and we will get the key. So I'll create three variables. One is for start, that is 0. One is for and, that is at n minus 1. And why I'm taking n minus 1? Because n minus 1 is the index of the last element. Okay, so if you have n elements in an array, then last element is at n minus 1. So then we said we will do some work while start is less than equal to end, and if start exceeds the value of end, this will break the loop. We will come out of the loop and we can return -1. That means the element is not present. So first we will compute the midpoint, that is start plus end by 2, and then we can do a comparison. If array of mid equals key, that means it is equal to the element that we are looking for, then our answer is nothing but the index mid. But if it is not the case, if array of mid is greater than what we are looking for, okay, so let's say at the middle we have 15 but we are looking for an element 3, okay, so in that case what we should do, we should reduce this part of the array. So that means the end which is pointing here should come here. So that means end should be equal to mid minus 1. So let's say end should come to mid minus 1. Otherwise the array of mid is smaller than what we are looking for. Let's say the middle element is 15 and we are looking for 20. In that case what we should do, we should discard this part of the array and this start should go here. This start should come to mid plus 1. Okay, so let's say start equals mid plus 1, that's it, and this will go on, and finally what we will get, we'll get the correct index. So I've built the code and let us try to run it. So / binary search, let's search for an element, let's say 30. So it should be at index 2. Yes, it is correct. Let's search for 70. So we have 0 1 2 3 4 5 6. So it should be at index 6, which is fine. Let's search for 89, index 7, and let's search for, let's say 77. So it says 77 not found. That means all our queries are working as expected. So one last thing I want to talk about is how much work we are doing in terms of time. So we are going to talk about time complexity. Okay, how many iterations this loop is going to take. So we have, in the first iteration we have array which is of size n. So we can say this is nothing but n divided by 2 raised to the power 0. Okay, that is 1. In the next iteration this array is reduced by a factor of 2. Okay, so we are decaying this array by a factor of 2. So that means let's say this is iteration 0, iteration number 1, it is n divided by 2 raised to the power 1. In the next iteration it will become n by 4. That means it would be n by 2 square, iteration number 2. And after, let's say, k number of iterations, okay, the array size would become n by 2 raised to the power k, okay, and that should be equal to 1. Okay, so after k iterations it would be equal to 1 because we are left with 1 element or 0 elements. So after k iterations it would be n by 2 raised to the power k, and it must be equal to 1. So what we can say, how many steps, how many times this loop is going to run. Okay, so we are doing a constant work here. This work does not depend upon the value of n, but this loop depends upon the value of n. Okay, so we can say n by 2 raised to the power k, this is equal to 1. That means n is equal to 2 raised to the power k, and we can say k is equal to log of n. Okay, so so this loop is going to run log of n times, and that is why you will come across this term that the time complexity of binary search is order of log of n. So this loop is going to take log n iterations. Okay, for example, if the array is of size 16, then it will become 8, then it will become 4, then it will become 2, and finally it will become 1. What is log of 16 to the base 2? So it is equal to 4. So in exactly 4 steps we can find out where this particular element is present inside this particular array. That is going to be the worst case. For example, if n is 1000, then log of 1000 to the base 2 is approximately 10. Okay, that means in an array of size 1000, in just 10 iterations you can figure out where a particular element is present. So binary search is very fast and efficient algorithm, but it works only if your search space is a sorted search space. Okay, so the only condition required is your search space should be sorted, or in other terms we can say the search space is monotonic. Okay, so monotonic means the values should be either non-decreasing, you can have a search space like this, or they should be non-increasing. Okay, the values should either decrease or they should remain same. Only then the binary search will work. So monotonic means non-decreasing or non-increasing. Okay, so this curve is a non-decreasing curve, this is a non-increasing curve. Okay, so in this example we can say all the values are in increasing order, and we could use binary search in this particular example. So I hope you understood the concept. See you in the next lecture.